First of all, I'll tell you more about myself. Like, I'm community manager for Gensim. Gensim is a topic modeling open source project. If you're here for the previous talk, you've seen topic modeling applied to Channel 4 viewer data, which is very interesting. We also have other algorithms rather than just topic modeling itself. We also have word embeddings. It's two parts of Gensim. It's topic modeling and word embeddings. So I will talk about word embeddings today. And the package is used widely throughout industry. We have many industry adopters. And at the same time, we have about 500 academic citations. So we are at this intersection between academia and industry. That's what we do. We take some academic paper, maybe it comes with some C code, and they have variable names like alpha and gamma and no comments. And we turn it into Python code with some maybe C extensions and make it easy to maintain, easy to use, something which can be used in production. And we have a mailing list and active community. We also have a coding sprint today at 1:30 in the afternoon where we'll ask people to come in and go through our tutorials to find if they can improve our tutorials, maybe fix some small, easy bug issues. So you are welcome to join if you're interested more in topic modeling or word embeddings. So I'll talk about more later. Cool. So the credits for this talk go to a student. We have a student program where we mentor students around the world. It's a remote program. So this work has mainly been done by Parul. She's an undergraduate student at University of Delhi in India. Like we met every week for half an hour on Skype for several months, and she created most of the things that I'm going to be talking to you about. And in general, we have a large incubator program. Have many students. If you're a student here who's working on a master's thesis, please come to me, talk to me afterwards. It'd be very nice if you want to publish a blog post about it or contribute to open source as part of your education. Cool. Okay, so let's come to the main part of the talk. So which words are similar? So I'll show you a pair of words, and you'll tell me if they're similar or not. So coast and shore, are they similar or not? Like if you think they're similar, raise your hand. Okay, so most people think they're similar. And okay, I agree they're similar. Can you tell me why they're similar? Huh? They're like the same? The sea. They're coastal things, but there's a difference between them. They have a different meaning, yeah? They're used in the same context, okay. Any other definitions?
The interface between the sea and the land.
Okay, they have the same definition. Okay, they have the same meaning. The context is the same, but also the meaning is the same.
Only as nouns, though.
Okay, they're nouns. Okay, that's something in general between them.
As verbs, they're different.
To shore something,
yeah.
or okay.
And to coast.
Oh yeah, and to coast, exactly. Yeah, to coast is like to drive like in a relaxed way. Yeah, without any effort. So they're different in some way. Okay, so maybe as nouns they're similar, as verbs they're different. That's hard. Okay, what about clothes and closet? Are they similar?
No.
But like, I put my clothes in the closet, they're related. Like you have a website called closet.com, it's about clothes. They're not similar? Okay, who thinks they're similar? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and everybody thinks they're not similar. It's an easy choice. So they're similar in the sense that they're related. They're on the same topic. And that's like clothes versus shark. That's a different words. Clothes and closet, they're similar, but they're also different. Okay? And another way I can say that they're different. And why is because they're not interchangeable. You can say like, I put on my clothes. I cannot say I put on my closet. So in that sense, they're different. And the context in which I use them is also different. I cannot say I can put on my clothes or put on my closet, but the topic is the same. But they're different. So it means I have two different notions of similarity here, at least. One of them is about topic, another them is about how they're interchangeable or not interchangeable. And these things, they can answer different business problems. Depending on what you want to be answered, you have to define what similarity you want. And like this, if you want to, this is from Pride and Prejudice. Like there's two business problems you can ask about Pride and Prejudice. What does Elizabeth think about Mr. Darcy? Which is like a general, broad topic question. Or you can want to know what are male characters in Pride and Prejudice. And that's a very specific interchangeable word question. What are the words I can interchange for Darcy? And then you can find all the male characters that way. And in serious business, you would have this kind of business questions. What are words in the topic of Darcy? Or what are the named entities in the text who are male? And you have to use two different notions of similarity to answer these two different business questions. And today I'll talk about different algorithms and different hyperparameters you can do to find this for similarity algorithms, and you'll be able to tune them to choose which similarity you want. So you know which algorithm to pick and which hyperparameters to use. That will be the purpose of today's talk. Okay. So this is an example of two models trained in Pride and Prejudice. And this first one is the blue is just a topical model. It shows you the attributes of Darcy. And you see that there are things like smile, composure, surprised. This is just a general topic of Darcy. And the second model is for interchangeable words. What are all the male characters which are in the book? And you see like Mr. Wickham, Mr. Bingley, and other male characters which are there in the book. And I'll show you how to train these models later. How to get the hyperparameters to get this to different kinds of similarity. Any questions so far? No. Cool. So this is an example of something which is trained on a bigger corpus than just Pride and Prejudice. Pride and Prejudice is just a couple of 100,000 words. And this has been trained in Wikipedia. Wikipedia is 17 million words, and there you get much better matches. So there's 3 different algorithms, and you get 3 different kinds of similarity. So if you use WordRank, you get attributes of a king. And if you use Word2Vec, you get interchangeable words of the king. And if you use fast text, you get a mix of 2 that way. So you see for WordRank, you get throne, because king sits on the throne. You get king was crowned, monarch, things which are in the general topic of the king. Similar to how clothes and closet are in the same topic. That's what you get from WordRank. From Word2Vec, you just get names of kings. And these are the things that are interchangeable with king. Just how you get Darcy, you get other male characters, or coast and shore, they're quite interchangeable in that way. So you get the interchangeable similarity. Or in fast text, you get a mix of both. So these are the 2 kinds of similarity described in literature, mainly. So let me go into the theory first, and then I'll go into the code, how to run this stuff. So, OK, so what is a word embedding? I've been using that word for a while. And the word embedding is a way to assign a vector to a word. In general, if I have a word, there's some very easy way to assign a vector to it. I can just have a one-hot embedding. I have a vector which is 1 million numbers long, and I have 1 million words in my vocabulary. I take just 1 million numbers long vector, and I just do one hot embedding. So I turn on the first bit if it means the first word. For king, it will be my first word. Just turn the first bit. Queen will be my second word. I'll turn on the second bit for the queen, and the rest of them will be zeros. So I have this really long vector which only has 1 non-zero entry. It's called one hot embedding. That's the easiest way to just embed so many discrete values into a vector. And the annoying thing here is that it's really long. You just have to store this million numbers in memory. And also, I cannot really see the similarity between words. King and queen, I don't know if there's anything. King and queen look very different, the same way as like king and book look very different. There's no information about relationships between the words in here. That's not a very nice way. There's no semantics, and it takes lots of memory. Well, you can say that. So the solution to that is to have a small representation. Just pick 3 dimensions or 100 dimensions. But there you're not going to have 0 and 1. You're going to have real numbers in there. So you have like 0.94 for king, 0.57, 0.22. Just some numbers in there. And word embedding is this called a dense representation of words in a low dimensional vector space. So it's not going to be as high as this. It's going to be usually 100 dimensions or 300 dimensions. Those are the usual number of dimensions people choose for the word embeddings. And when I say word embedding, it's the same as saying a word vector, or same as saying distributed representation. And distributed representation, it's not nothing to do with distributed computing. It's the only connection. Meaning of the word distributed is that the meaning is spread through these 3 dimensions here. It's not just concentrated in the first one for the king. It's just spread across all the 3. So there's no one axis in there which is the king axis. It's usually spread across all the 3 of them. That's what it means for distributed representation. Cool. Any questions on the definition so far? OK, cool. How many of you have seen word embeddings before? OK, most of the room. Cool. So I can move slightly faster for the theory then. Okay, so this is a very nice visualization. You can do it in TensorBoard. Gensim has ways to convert all the Gensim models into TensorBoard. You can take any Gensim model and plot it in this nice way. This is TSNE from 100 dimensions to 3. And I tweak the parameters of TSNE, I get something slightly different. I do PCA, I get something slightly different. I don't really believe in these visualizations very much. Like, I believe in this table much better. But I cannot bring it to a client meeting. I have to bring something as fancy as this, which is rotating, and it's quite cool. But you can see like the king is here, and like regicide, and royalty, kingship. Like these words are really like somewhere nearby. Yeah, but the closest 10 words not always appear on this graph as the closest 10 words to the king. So it's kind of nice to see if your model makes sense. But I wouldn't rely on it as my main tool. Like I would much more rely on tables like this as my main tool, which is just to calculate the closest words. And this is something that I would rely on. But it still, shows you the idea that like how I get the vectors for the words, and they all float in this space. Just this is an illustration of what word embedding is. Cool. Okay, so the question is how to come up with these vectors. So how do I find a good vector for king and a good vector for queen? And I need to get a co-occurrence matrix. The credit for the slide goes to Ed Greffenstadt. It's from a very nice Oxford course on deep NLP. It's better than CS2-4D. Yeah, it's the next level of that. So if you haven't looked at it, please look at the Oxford CS Deep NLP 2017 course. It's really nice. So, OK. So to come up with a vector, I have to start with some information about my text. And previously, somebody said that closed and show are the same because they appear in the same context. And context is very important. I'll show you how we work with context here. So these are I have 4 sentences about cats and dogs, of course. So in the cute kitten purred, about something about a cat, another sentence about a kitten, and then about a dog. And I extract the context from my corpus. So kitten appears next to cute, purred, cute again, and then meowed. So cute, purred, and meowed, they are the context words of kitten. So those are the things that it intersects with. In the same way for the cat, and in a similar way for the dog. The interesting thing is that cute, the kitten is cute here, and kitten is cute here again. So cute appears twice as a friend of kitten. Like as a neighbor of kitten, they appear twice. So let's turn this into a matrix. So the matrix will have the context words this way and the central words this way. So I have kitten and cute. So kitten and cute appear twice together in the same sentence. And I think, oh yeah, meowed. Meowed didn't make it, and purr didn't make it, but yeah. So I have cat. I have cat and furry appearing together. It was a cute cat as well. And there's dog and furry appearing together. And that's already, if I just take this row, that's actually a very nice representation of a word already. That's actually quite good. Because I can see that if I do, like, say, kitten and cat, they have cute in common. And dog and cat, they have furry in common. So I can see that they're somehow related. And probably kitten and cat are more related than the dog and cat. If I just look at what are the common features that they have. So that's already quite good. The only problem with this is that it is, my length of it, like this way length is my vocabulary, but that's fine. And this way the length is also all my context words. So it's going to be a million by million again. So it's going to be a really big matrix. That's the problem with this matrix already. So I have to do some dimensionality reduction. So I start from my co-occurrence matrix here, which is my X, and it's really big. And just, dimension is vocab by vocab. And I want to factorize it. Factorizing matrices is what they teach you in linear algebra course, and people have been doing it since the 70s. It's a very old technique. Just take a matrix and factorize it into something smaller. Usual dimensionality reduction. So I have, dimensions will be vocab times small, and small times vocab. And the row in this matrix will correspond to the words. So the first row will tell me something about the kitten. That's all that's happening in all word embeddings. Yeah, there's some interesting story that it wasn't always obvious that that's what's happening in all word embeddings, but I'll talk about it later. Cool. So the only question is how to come up with these two matrices, what they should be. There are many matrix factorization algorithms out there. So in word2vec, I want my co-occurrence score to be, say, the dot product. It's more like PMI, and there's some other terms in there, but just let's assume for today that it's just the dot product of some vector for the word and the vector for the context. That's all I want to get in word2vec. Just want the dot product of these two vectors to be somehow related to their co-occurrence count. So kitten and cute appear a lot together, so this should be high. And dog and cute never appear together, so that should be low. That kind of logic should happen here. Cool. So that's the logic of word2vec. I just have, for vector, I have one word, and I have for one word I have one vector. Yeah. And fast text is another algorithm. It's another word embedding which came out in August from Facebook, and it was present before in Wopal Webbit, and you can probably do it somehow yourself. But it's really gotten more popular since August. Cool. And there they use this trick where they don't look at words, they look at subwords. And OK, this didn't make it on the big screen. So there should be u_subword.v. So it's just a sum. You sum over all vectors for all the subwords you have in there, and dot it with your context word. So you no longer look at have one word, one vector. Here you have one word, many vectors. And for example, if I look at the word going, I'll have many vectors for that. I'll have go, have oi, have in, and g, gu, oin, and ing. These are all my 2 and 3 grams are there. And this is kind of like a poor man's morphology. Like if I'm a human, like I look at going, in school they told me that go is the root and ing is like the ending. Computer doesn't know that. Computer cannot do that. They didn't go to school. So all they can do is just like hacky way. You just like take all the combinations of letters in there, contiguous combinations, and see which one has the most meaning. And just like maybe if I like average all of them, I'll find something meaningful. I'll probably guess that go is like important root, and that will give me an important vector for that. And I'll probably ing will have a lot of meaning for me. But I'll just figure it out by trying all the combinations. It's a poor man's morphology, this thing. Just n-grams is a poor man's morphology.
Why do you have G with 2 O's?
Oh, yeah, that should not be there. That should be GOE. Yeah, you're right. GOE, yeah, that should be GOI. GOI. Thank you. So these are more examples. Yeah, these ones are correct. They don't have any mistakes, I think. Cool. So fast text is better than word2vec because you have morphology. Because you don't have one vector for a word. You have many vectors for a word for many different parts of the word. And you can, all these words will be related. Go will be related to goes, and going will be related to go, because they'll have this subword go that they all share. Yeah, like it shows how they all share. And this is colored in green. The problem is this is slower. Instead of coming up with one vector for going, I have to come up with 1, 2, 3, 4, and many more vectors, which are just for the little subparts of that. So it means my runtime will be much longer, and that's annoying. And my vocabulary will be much bigger, and yeah. So it means I have to spend more time training my model. That is annoying. That is slower. Cool. But it is better at interchangeable words. There's, how we discussed there's 2 kinds of similarity there, and we have 2 different kinds of tests for them. We have just a list of words which are similar in a related way, have a list of words which are similar in an interchangeable way. And we can test our algorithms on that. So for related words, they are fast text and word2vec, they're the same. Yeah, when I said Gensim, it means Gensim word2vec. But for interchangeable words, fast text like blows everything out of the water if you use this n-grams. Because interchangeable words, night and nights, these are the kind of things you have in there. And of course, if you look at the roots of that, you'll be able to guess it much better than just thinking that night and nights are not related at all, and then suddenly if they appear in the same context, I guess they're the same. It's much easier to just look at the subwords than to think about context. Yeah, and that's why so fast text really wins at this interchangeable words accuracy. And this is, like you can see that this big graph. It's trained on a very small corpus, and in larger corpora it just gets more. Yeah, it still wins even in larger corpora. Cool. So this is the API for fast text. We have a wrapper, And it's the same things that you would use for word-to-vec embedding. Word-to-vec is old, it's been around for about 3 years. And you don't have to change your code much if you want to switch to fast text. You just use the same API in Gensim as you would there. It just maybe take you longer to train. And you have to install fast text. But Gensim API is the same. And you see, I can check if the word nights is in my vocabulary. Have I trained it with the word nights? No. And the answer is false. So it says never seen the word nights before in training. And the only word I've seen is night and some other related words. But if I look at the similarity of night and nights, it can still answer it for me. Because some of the n-grams, some of the little bit subwords of nights are contained in my training set. And specifically night is there. It's seen night during training, so it can guess that nights is related to night. And it gives me 97 similarity. So given similarity is very high for them. And word2vec cannot do this. Word2vec is like a fixed vocabulary technique. You cannot add new words to it. And specifically, even if you add new words to it, you have to train it for a long time to explain to word2vec what these new words mean. But fastText just guesses it because of they share some subwords, and that's how it works.
What kind of similarity would it show if you gave it night with a K?
If it's never seen it before?
Night with a K, obviously spelled.
Oh, yeah, actually, because
So would it equally show like 93%?
yeah, it will show that they're quite similar. Yeah. If you train it on a small corpus. If you train it on a big one, then the context will take over. But if you train it on like 1 million or like 500,000, then yeah, it will show them as similar, which is unfortunate. Yeah, I should add night here as an example of a K. Yeah, for next one. Cool. Any more questions?
So I didn't hear them on the front. Maybe this is the same.
Mm-hmm.
Does it introduce a problem if you have like conservation and conversation? Are they going to be shown very close?
The switching around doesn't work for that. Like the fact that they can call con and shin, that might be there, but the servation and versation, they're very different. So I would expect them to be quite different. Yeah. But
I think that the use of English to perform this sort of experiments will become quickly sort of limiting, because English is sort of clean with verbs.
Yes.
And it has a very easy structure.
Yeah.
If you get, I'm Italian and I studied a little bit of French, and in those two languages, for example, you get a lot of the in verbs you get a mess but from that mess you could actually get from small n-grams you could get like what's the tense if it is in the past, if it is in the future, who is actually doing that. While actually I don't know, Italian now is a language from like the 60s. Is actually a language because of television, but still there are like very dialects, but dialects are mostly something like that influence and change.
Yeah.
So you could have things location that leaks into the...
It is cheating. Like using this thing for English is really cheating. English has very simple morphology compared to other languages. And fastText, the Facebook team has released 78 trained models on 78 languages from Wikipedia, and the more complicated morphologies for that language, the more fastText beats word2vec there. So it's definitely not designed for English. It's designed for languages with complicated morphology, like Russian or Polish or Portuguese or Italian. Yeah, so definitely English is not the best example, but it's our common denominator in this room. So that's the example that I like to show you. Yeah, there was a nice talk yesterday about fastText for French and Russian and translation by Babylon Health. Cool. So I already mentioned that this is slower, that fastText is slower than word2vec just because you have more vectors that you need to come up with. But the weird thing is, even if I disable this feature of like having any vectors to come up with, it will just say like only think about words. And I have these two algorithms. They should do exactly the same thing. One is written in C, fastText is written just pure C. Another is written in Python with a little bit of Cyphon, bits which are computationally intensive in there, and they should run the same. And actually, C, is perceived as a faster language than Python, but somehow Python runs faster. And and if I disable all the n-gram feature, if I just say like the maximum subword you should use is 0 length, and just do words vectors for word here, vectors for there, and then somehow C is still slower than Python, and and PyData, I'm happy to share this with you. It's not by much, but it is still slightly slower. Yeah. Cool. So we described 3 ways to get a vector for a word, but generally there are many ways to do that. So we just talked about word2vec, fast text, and now I'll talk about WordRank third. There is just a much simpler ways to just factorize the metrics. I could use, SVD, or it's just called LSI if I apply SVD to a co-occurrence matrix. And that's a nice thing to do. It's been around since the 70s. There's nothing new about it. And, oh yeah. Does anybody know when word2vec paper was published? 2012, yeah. And it was published by Mikolov. Mikolov is a deep learning guy. He's just a deep learning researcher. He saw some paper where people were coming up with this word vectors in a very complicated deep learning way, and he just come up with a simpler way to do it. Maybe just use a 1-layer network, and that will just be enough. That was the purpose of his paper. He didn't know anything about natural language processing and all these co-occurrence matrices and distributed semantics. He just had a neural network model. And if you read his paper, there's nothing really about co-occurrences in there. And then later, Levy and Goldberg, they proved that doing this neural network thing is the same as factorizing a co-occurrence matrix in some way. So they linked it to all these old techniques that have been around since the 70s. But word2vec became popular just because the code was there, it was fast to run, there was a paper around, and it just worked. And that became a very popular algorithm, even though the similar things have been around for a long time before. But if you release your paper together with a nice code, which is performant, then you will become popular, even though some algorithms have been before for a long time. Yeah, for hundreds, but like tens of years. Yeah, and now we'll see it all in perspective, how they're all trying to do the same thing, just by factorizing this, factorizing this co-occurrence matrix in different ways. So there are other embeddings out there: glove, swivel, eigenwords, and var-embed. They're all doing very similar things. Var-embed is interesting because var-embed actually has an honest morphology. You have to have a morphology package which extracts the roots for you, and then you can do embeddings based on morphology. Yeah, that's quite nice, but it takes a really long time to run. That's the only problem with that. You're not just doing morphology. Honestly, it's harder than just doing something hacky by taking every 2 or 3 letter combinations from inside of your word. Cool. So let's move to WordRank. So WordRank is a ranking algorithm. Word2vec is a classification problem, and WordRank is a ranking algorithm. So in Word2vec, I have my context, cute, and I want to predict what's the most likely word in that context. And the word that's just most likely is kitten, because kitten appears with cute twice in my corpus. So okay, cute is the best friend, is kitten. So I just want to find out how one word is an input, one word is an output. That's what Word2vec does for me. WordRank thinks about it differently. And when it gets a word cute, what it wants to produce out is a ranking. So I want to produce a list of words where the first one is going to be kitten, because cute and kitten appear twice. Second is going to be cat. Cat was cute once. And the third one is going to be dog. Dog was never cute. So it'll be just the third one. And the loss function here is quite robust. If I make a mistake at the top, that costs me a lot. If I make a mistake at the bottom, number 10, 20, I don't care about it that much. And that makes it much more robust to noise. If some things randomly appear together, and that mistake happens at the bottom, I don't really care about that. But if things appear together very often, that's very important to me. That's probably the main meaning of the word is there at the top. And it's a different formulation of the problem. And you can use the whole of learning to rank methodology there. Like, I didn't know about learning to rank until I discovered WordRank. It's a very nice area, and you can apply it to many different problems, actually, in data science. Has anyone heard about learning to rank before? OK, 1, 2, 2 people, 3. OK, 4. OK, so maybe it just was special to me. But yeah, you should check it out. Some tutorials on LTR. And it does very good results for the word embeddings. We have a WordRank wrapper. The API is the same as for Word2vec. Just train it as the same way you would train Word2vec, and it gives you the most similar words. And you can see, like, when I use any model, when I use Word2vec, I still look at the ranks. So the way actually word embeddings are used, it's really a ranking problem. And it's a very natural definition of the problem is to think about it as a ranking. Because usually I just look at most similar, and what are the most similar, 3, 5, 10 most similar words. That's how I validate them. It's been trained on a small corpus, like all the Lee corpus. Yeah, and this is the results that you get for that. But the API is the same, so it's very easy. If you want to switch to word rank from word to vec, you don't need to change your code much, just how you train it. But their query code will be the same in Gensim. Cool. Yeah, okay, there's more 3DVs in TensorBoard. Now it's a word rank embedding, which is slightly different. Cool. So let's do some evaluations. So this is when it was trained on 1 million corpus. OK, I have 5 minutes to go. And on 1 million corpus, you can see that word rank takes 4 hours to run. It's a much harder problem when you want to predict the whole rank around just one word. And other things are just seconds, less than a minute. And does many passes. But even on a small corpus, 1 million is a small corpus, I get really high accuracy for related ones. The related things are close and closed. This kind of similarities come up really well here. It's because of I think the nature of ranking that it's quite it looks at quite a large context around it. Yeah, the interchangeable accuracy is not so good for word rank, but the related ones, that's where it beats the other things out of the water. For example, to get something like the initial paper claims that if you have 17 million words, you get the same related accuracy as if you trained word to vec on 17 billion. But so you can get the same result, but on a smaller corpus with word rank for related similarity. If you care about just general topics, you should use word rank. And I'll have a decision tree in the end which shows you what to use when. Well, this is 17 million. This is Wikipedia, and it takes 40 hours to run word rank on Wikipedia, while the other things are just half an hour, definitely under an hour. This is seconds, and this is hours. OK. Yeah, and here related accuracy for word rank is still the best. Still very good at related ones. Even fast text is coming up close, and interchangeable is fast text is coming up close as well. Cool. OK, let's talk more about hyperparameter tuning. So the window is how far left and right I go. So when I have the kitten in the middle and it says cute kitten jumped over the fence, sometimes I have cute and jumped as my neighbors of kitten, or if I want to have a window 1, for example. If I want to have my window 3, then I have cute kitten jumped over the fence. They're all going to be neighbors of kitten. So it depends how far left and how far right I go in my documents to see what are the neighbors of that word. And you can see how things change as I increase the window. For example, when I train this model for interchangeable words, I use a very small window. Because I use it like Darcy, road. It's the same like Darcy road or Darcy said or Darcy moved was the same way as like Bingley moved or Bingley road. I had this male adjectives next to the male name, so I only looked like two words left and two words right, and that's how I got the interchangeable model for Pride and Prejudice. And if I look at the bigger window, I get less interchangeable stuff, but I get more related stuff. So you can see that. As the window is growing, so I have like 2, 15, 50. As the window is growing, my related accuracy is growing, so it becomes more topical. If a doctor in like the profession of somebody appears, usually it's like 10 words away from the actual name. But if they appear together a lot, then they will become closer together. And the interchangeable accuracy goes down as I increase my window. So depending on what accuracy you want, what similarity you want, you have to choose the window appropriately. And that's true for word to vec, it's true for far text. For word rank, it's not so sensitive to this parameter. Word rank just focuses on related mainly that way. So yeah, this is quite a nice thing to play with. So interchangeable, small window, related, big window. Cool. So this is a table, how to get similarity you need. So if you want to find something related and I want to describe the word's topic, and I want to know what the document is vaguely about. Like I want to know which department should I send the support email to. Then I should use word rank. Even on a small corpus, it would work quite well. Or word to vec if I have a big corpus with a big window. Or if I find named entities in the text, I want to find what is similar to Java senior developer. Specifically, is it the same as lead Java developer? Then I would use interchangeable stuff. And I'll use a word to vec skip around a small window, fast text, or var embed. OK, and this is a decision tree for the same table. So my similar words are related, and I got 1 million words. Yes, use word to vec for large context. No, I have something small. Word rank is your best shot that way if you want something related. Interchangeable words, yeah, you use any one of these 3. And fast text should be your first choice nowadays. Like in a year from now, I think nobody will be using Word2Vec. Everybody will be using fast text. And yeah, I think so. It's a nice thing. Cool. Yeah, so thanks for listening. We'll have a coding sprint today. If you want to contribute to open source or just learn some NLP yourself, it would be very nice if you come in, try to run our tutorials. The tutorials were designed for version which was 6 months ago. It might learn a Gensim, some of us would work Gensim 2.0, some of it might not. But just it'd be very helpful for us if you run for them, and maybe some things you don't understand, and we explain it to you and we change the tutorial better, like link it to Wikipedia or something. So yeah, if you want to learn more about NLP, please come to the sprint. Or if you want to do more advanced stuff, you're welcome to fix some easy bug on GitHub. Or if you want to do your wonderful work for full fact yesterday, which you did, Dave here, yeah. You can do that. You can turn that into a Gensim tutorial. That would be quite nice as well. Cool. Now we have time for questions.
For the word rank transformation, what's the similarity measure they use? Because it didn't seem obvious to me that the vectors are going to be in a vector space with the word rank. Like you couldn't do a cosine similarity.
You still do cosine similarity.
Okay.
Yeah. When you do similarity, it's still cosine. It is the same method as before. Your objective function is just designed as like a sums over all the words and over rank, and emphasizes the highest ranking words that way. But it's still cosine. Any more questions? Yes.
When you have Word2Vec, and you expand to sentences, you do average or doc2Vec. Are there any tricks or methods for fast text?
Yeah, you can still do average. Average works for anything. You can do average with fast text. You can average with word rank. There's no specific tricks out there. Yeah. I haven't heard of doc2vec with n-grams, but you can probably do doc2vec with n-grams as well. You just split your corpus into n-grams before and feed it to doc2vec. You can have fast doc2vec, even though it is slower, but you can call it that way. Yeah. Any more questions?
I just wondered how
Yeah?
similar these are. If you've got 1 million words, can you sort of do it on small scale on Word2Vec, and then once you've decided what you want, then switch over to word rank and do like the 50-hour training later? Or would you tend to use just one of these, or would you start with one of the faster ones and then go to word rank later if you want something that's better? You might go down a completely different path with Word2Vec. And then when you switch to word rank, you think it's something different. I don't know.
Yeah, like if you train it on Word2Vec and you get this, your accuracy that you get, and usually you have this is unsupervised training, so it's very hard to evaluate it intrinsically. You only know how useful it is somewhere downstream. So you have some supervised problem down there, and you train your Word2Vec model on 1 million words. It's really fast, and you see my accuracy did not increase at all. So then I would give up and not do anything. But if I see it increased at least by 0.5% or 2%, then okay, maybe word embeddings are useful here. So I would go more into this route and train word rank for a long time and see what's happening there. Yeah, so it is definitely a right path to just try word embedding if it's useful for you. Because sometimes, if my corpus is quite small, TF-IDF works really well. And I don't need to go to anything advanced as this. So I have TF-IDF, just fast, and then I add Word2Vec and I see nothing has changed. Okay, so I probably don't need word embeddings here. Yeah, so it's a good exploration path. I agree.
You always go fast text rather than Word2Vec.
Yeah, it's just because of habit. Like fast text has been around for a year, and Word2Vec has been around for 3 or 4 years. Just because of habit, I go to Word2Vec first. But you can easily go to fast text first. It's not that much slower. Yeah, in general. But yeah, just use more fast text. Cool. Any more questions? Yeah, awesome. So yeah, see you all later at the sprint today.